going to demonstrate the working principle and operation of the Curiepoint pyrolyzer coupled with the gas chromatograph mass spectrometer. We are here with the Curiepoint pyrolyzer JHI07 from JI Japan, connected to a GCMS from Shimadzu Corporation. Analytical GCMS is used to study the thermal decomposition of a wide range of materials, including polymers, plastics, biomass, solid wastes, and also liquid samples that are reactive in nature. I am using it for jet fuel pyrolysis to understand the nature of decomposition of aviation jet fuels under high temperature and high heating rates. The information we get from such an analysis will be valuable in the design of novel hydrocarbon fuels. In Curiepoint pyrolysis, a ferromagnetic metal alloy foil, also called as pyrofoil, is used to contain the sample. The pyrofoil is placed inside a coil of high frequency oscillator, producing an oscillating magnetic field. The pyrofoil is transformed into a magnet via electromagnetic induction. If the direction of the current of the coil is changed, the polarity of the magnet is reversed and heat is generated. Owing to this unique way of heating, only 0.2 seconds is needed to attain the Curiepoint temperature. The ferromagnetic property of the pyrofoil is lost as soon as it reaches the Curiepoint temperature, and the temperature remains constant afterwards. The Curiepoint temperature is nothing but the pyrolysis temperature of the sample, because the sample is in intimate contact with the pyrofoil. Curiepoint is the function of the composition of the metal alloy. For example, high proportions of iron in the alloy leads to a higher Curiepoint temperature, whereas the high proportion of the nickel in the alloy results in a lower Curiepoint temperature. Pyrofoils with Curiepoint temperature in the range of 160 to 1040 degrees centigrade is available with us. Pyrofoil is placed at the top section of the pyrolyzer, where it is attached to a magnetic knob. The pyrofoil falls to bottom as soon as the knob is pulled. Pyrolysis starts automatically once the fall is detected. Pyrolysis time can be varied from 1 to 99 seconds. Pyrolyzers are then swept by the helium gas to the hyphenated GCMS system, where the compounds are separated by a dV5ms GC column based on their boiling point and affinity for the column material. The separated products now enter the MS, where they are fragmented into ions and are identified based on charge to mass ratio to give a characteristic mass spectra. The mass spectra is recorded and compared with the NIST library. The ion current is recorded as peaks in the chromatogram. The sample preparation involves placing 1 microliter of the liquid sample in the pyrofoil, followed by the crimping of the foil using flat nose pliers. This ensures intimate contact of the fuel droplet with the pyrofoil's inner surface. The injector temperature of the GC is generally set at 350 degrees centigrade. In a typical GC oven program, the column is initially maintained at 40 degrees centigrade for 1 minute, and then it is heated to 260 degrees centigrade at a rate of 5 degrees centigrade per minute, and then finally maintained at 260 degrees centigrade for 2 minutes. For MS, the electron ionization voltage is 70 electron volt, and ion source and interface temperatures are set at 250 and 300 degrees centigrade respectively. The mass range scanned for a jet fuel is typically 19 to 500 daltons. The peaks are identified using NIST 14 and Wiley 08 libraries. After the methods are selected and set temperatures are reached, the knob is pulled to start the pyrolysis run. This also triggers the GCMS system, which starts analyzing the incoming product gases. The chromatogram generated from the experiment shows the peaks of the pyrolysis products. The x-axis is the retention time in minutes and the y-axis is the intensity in picoampere. The software generates the table of products with corresponding peak area percentages and the library match factors. The peak area percentages help in understanding relative abundance of products, which serve as important starting points to build reaction networks and generate kinetic data.